Okay, so I'm going to go over an example of non-dimensionalization, and I'm going to use the 2D Navier-Stokes equation. So here I have the equation for the x direction of the 2D Navier-Stokes equation, and to begin with, we first want to look at what would be our non-dimensional variables that we'll use to replace the variables in this equation for like Vx, t, x, y, and so forth. So here are the non-dimensional terms that we're going to use, and I'm labeling all of them as the variable starred. So Vx star would equal to Vx divided by the average velocity in the x direction. Same goes for Vy. We're normalizing by the average velocity in the x direction. X star is going to be equal to x over L. Y star, y over L. Our Gx star is the gravity in x direction divided by the gravitational acceleration. And our pressure, a normalized pressure, is pressure divided by rho, average velocity in the x direction squared. And finally, our time is non-dimensionalized by capital T, in a lot of cases the frequency. So we're going to use all of these variables, and we're going to just end up plugging them into the equation. So if we need a Vx right here, we're going to use this equation right here, where Vx is going to be equal to Vx star times the average velocity in the x direction. Just plug it in and use all of these to plug in the variables and to get our non-dimensionalized equation. So let's start off here just looking at this left hand side, and we're going to go through and try to non-dimensionalize each one of these terms using these. So if we're looking at Vx divided by or dvx divided by dt, it's going to look like we're just going to plug in again Vx, which is Vx star times the average velocity in the x direction in the place of the Vx, and do the same for our little t, our time. And now we can go ahead and pull out our average velocity in the x direction and our capital T, which is the frequency of period. And now we have our non-dimensionalized term. So again, we can do that for dvx over dx. Do the same thing, plugging in our two terms here that represent Vx. Same for x, and we can pull out the terms, and this is what it's going to look like for that term. Basically the same thing, but now we have it for y. And the other two terms in this equation, which is Vx and Vy. So these are all of the terms on the left-hand side of the Navier-Stokes, now non-dimensionalized. So let's go ahead and put all these together and plug it into here and see what we get. So now the left-hand side of the Navier-Stokes equation non-dimensionalized. So this left-hand side non-dimensionalized is going to look like this, where we just took what we just did and plugged in each one of these into the equation. So now we see we can rearrange some of these terms because we have the same things in each one of these, and when we rearrange it, we get this equation right here. So this is the left-hand side of the Navier-Stokes two-dimensional equation, non-dimensionalized. Now let's go and look at the right-hand side. So I'm going to start off right here with our pressure gradient. For non-dimensionalizing that term, again, we're plugging in our right here. Our pressure is going to be P star times rho, average velocity in the x direction squared, and then of course x is equal to x star times L. And we just pull our rho, average velocity in the x direction squared out divided by L, and this is our non-dimensionalized term. I'm going to do the same for the d squared Vx over dx squared. So now we're working on this part, and so when we break this one down, it's just going to be d over dx star L, and then we plug in our Vx, which is Vx star times the average velocity in the x direction divided by our dx star L. And again, we pull out our terms. We have the average velocity in the x direction divided by L squared. You can do the exact same thing for the second term of d squared Vx over dy squared. And you see you get similar terms here, except you have the x and the y. Finally, our gravitational force Gx is equal to Gx star times gravitational acceleration G. So we now are just going to put these terms into our equation here to see what we get on the right hand side. So here is the non-dimensionalized right hand side of the 2D Navier-Stokes, and I just plugged in everything that we just went over into the equation. So again, we can go ahead and pull these guys out and rearrange the equation a bit, and here's the equation rearranged. So now we have the left hand and the right hand side non-dimensionalized. Let's go ahead and put it together and see what we got. So this is our original 2D Navier-Stokes equation, and this is after it's been non-dimensionalized. There's one more thing that we can do to this, is we can go ahead and divide this whole term by both sides. So divide them by rho average velocity in the x direction squared divided by L, and we have this final equation for the 2D Navier-Stokes non-dimensionalized. And since we divided out our rho Vx squared divided by L, we can now see our non-dimensionalized our non-dimensional numbers that come into play. Right here, the Struhel number. We have our inverse Reynolds number. So you have your viscosity divided by rho Vx times L. So that's going to show you when you have a really large Reynolds number, that this whole term, your viscous forces are going to be negligible. So that's where it helps us to have a non-dimensionalized form here. So we're able to, just knowing the Reynolds number, we can start to neglect certain terms. So this is basic steps of going through of how to non-dimensionalize the 2D Navier-Stokes equation.